Version 6.0 of my direct granules extruder shown in the previous video is based on a threaded connector with a Teflon insert, which has resulted in very good print quality. Version 6.1 adopts this principle, the only change concerns the water cooling system. In previous versions I soldered a steel plate to the extruder tube and glued a 3D printed component onto it through which the water circulates. In the new version I use an aluminium block measuring 20x15x60mm with holes for the water circuit and for mounting the extruder tube. A 3D printed part serves as template for these holes. To fix the extruder tube, M4 threads are cut into the corresponding holes. The 6mm holes for the water circuit are sealed with PETG printed parts using superglue. When printing these parts, over extrusion should be adjusted to ensure they are watertight. The advantage of the new water cooling system is that the extruder tube is now only clamped in place with screws, allowing for quick and easy replacement. Furthermore, the extruder tube can be repositioned with this mount, allowing adjustment of the transition zone between the cold and hot end, a crucial parameter. The extruder with the Teflon insert works as good as the previous version. Anyone who wants to delve into the new technology of 3D printing with a direct granules extruder should first try building version 6.1, as this design proved to be very forgiving during my experiments. Printing with PLA allows you to take your first steps with granule printing and gain experience. Give it a try. However, Teflon wears out quickly, and this component also limits the maximum printing temperature to values below 220 degrees Celsius. So a full metal extruder was the next goal, which meant many more hours, days, weeks, even months of experimentation before I finally found a reliably functioning design. As mentioned in a previous video, the inner wall of the screw coupling is too rough after drilling out the thread, causing the powder to jam the extruder. Smoothing the inner wall was therefore necessary, and I did this in several different ways. Approach 1 was polishing the inside with abrasives of different grain sizes. Approach 2 involved coating the inner wall with enamel. And finally, approach 3 was to make insets from smooth steel sheets. All three approaches led to more or less the same results. Initially, the extrusion rate was nice and high, and the printing worked perfectly. But only after a few printed layers the extrusion rate dropped dramatically. The reason for this is that heat conduction along the tube causes the plastic to heat up through the extruder wall. This creates a lubricating film of liquid plastic in the transition zone. This in turn causes the plastic in this zone to rotate with the screw, which causes the extrusion rate to drop. So I tried gluing, soldering or enameling brake pads in the form of metal strips, but this didn't have the desired effect. The extrusion rate still dropped dramatically after a while. Aside from the smooth walls, what's the difference between the Teflon insert and my all-metal extruder tubes? Was it the groove instead of the metal strips that enabled the radial braking effect? So I polished a stainless steel tube on the inside, cut it open and inserted it into the extruder. But this version didn't really work well either. Teflon is a poor conductor of heat, and that makes another crucial difference. The plastic isn't heated by the extruder wall, so no film of liquid plastic forms here. So I bent and spot welded an insert from tin can sheets shaped to resemble the Teflon tube. An air gap between the sheet metal and the extruder wall provides thermal insulation. To shape the inserts from the 0.15mm sheet metal, I printed parts from PETG. A metal ring at the cold end ensures good heat dissipation. The metal tube is glued into the drilled out threaded connector. This bonding is done only on the metal ring at the cold end using superglue. The insert is cut off about 5mm above the connector and widened with another die to facilitate powder entry into the extruder. The design worked, but it was tricky to manufacture, so not every copy of this tube printed well. The results were also mixed in further tests with inserts with square or triangular cross-section or corrugated walls. So back to the drawing board, there has to be an easier way. The resulting idea greatly simplifies the extruder design. The tube now consists of a smooth walled tube, as in the initial experiments. A simple trick prevents the plastic from sticking to the screw and subsequently rotating with it in the melting zone. The wood screw acting as the auger is not positioned centrally, but rather so that it almost touches the wall at one point. On the opposite side, the gap to the extruder wall is correspondingly larger. This gap is necessary to allow the air trapped in the powder to escape and for pressure equalization to occur. The simple wood screw has a constant pitch and core diameter. When the film of liquid plastic forms on the tube wall and the material sticking to the screw rotates with it, the still solid core plastic is churned and transported further downwards. Here too, I had to conduct several experiments until I found a tube screw combination and extruder length that worked well. I'm using a threaded connector that's only 30mm long with a 6mm screw. The rough tube wall is again covered with a steel sheet. The transition zone from cold end to hot end is adjusted to only about 3mm. Now that it works, I'm asking myself again, why didn't I do it this way from the start? Many extruder tubes had to be made and tested to achieve this insight. Here again you only see a small selection. Version 6.2 of the extruder is currently planned to be the last one made using only simple tools. A CNC machine is already waiting in my workshop for future designs. Finally I carry out another test print with the new extruder design. I've printed enough chain links for now, so here's another Benchy. Printing is done with a 0.5mm nozzle. The aim of this print isn't speed or perfect results, but rather using two significantly different print speeds. Small parameters are printed at only 15mm per second, while all other structures are printed at 40mm per second. The acceleration is set to 10,000mm per square second. Compared to filament extruders, screw extruders have some unique characteristics which I will discuss in a future video. One of these is that the extrusion rate doesn't increase linearly with the screw's rotational speed. When transitioning from the window openings to the roof, the printer resumes printing with high speed after a long, slow speed period. However, it takes time for the necessary pressure to build up in the extruder tube. As a result, under-extrusion occurs, which manifests as gaps on the outer wall. Pressure advance is disabled for this print, but it would certainly be needed to be implemented differently than on filament printers. The chimney shows that the extrusion rate is proportionally higher at low speeds than at fast speeds. This structure is obviously printed with over-extrusion. There's still a lot of experimenting and fine-tuning needed to optimize the print results. At this point, a heartfelt thank you to all the wonderful people who have supported my experiments with financial contributions and continue to do so, whether through super thanks as a Patreon or via the donation button on my website. A special thanks goes to my anonymous major sponsor who provides me with significantly more than just peanut cans. Of course, the necessary files, photos and explanations for replicating this version are also available on my website. Thanks for watching and I'll be back.